Thank you for watching, and welcome to LAQV Webinars, a webinar series on topics of green chemistry. For more information, visit our website and follow us on social media.
Today, I'm going to present a little bit some insights of the electrochemistry and what it can bring into biomass valorization through oxidative enzymes. And this is just one aspect, one topic from the vast diversity of topics that we work in. And this time I decided to blink the eye to people of biomass and try to make them aware of the electrochemistry and how it can valorize the work. So, starting, as you all know, and naturally biomass is common renewable carbon source, okay, and it is considered as central to our energy transition and carbon neutrality that we are all searching for. And biomass can be, of course, used in several ways. For instance, cleavage with acid and basic strong media, but also it can be used with enzymatic catalysis, and this has advantage that it uses low energy and it can not only cleavage, but also convert the biomass for their reuse and added value products production. So just a small start for the ones that are not so familiar with biomass, and in particular lignocellulose biomass. So it is composed by cellulose here on the left, and hemicellulose in the central image, and lignin, which is a complex gathering of this type of compounds all together in very complex form. So we have in the biomass and lignocellulose biomass, we have strong CC and strong CO bonds, and this material is quite resistant to chemical breaking, and naturally, and that's why we see all the plants and all these material everywhere. So it accounts for more than 70% of the terrestrial biomass carbon. And if you see here, so we have fibrils and we have several layers in this lignocellulose, and of course, as I said, this is a very complex material, a very strong one, and the physical and chemical pretreatments, as I said, strong acid, strong alkaline, require a high demand of energy and also reagents. And also it can cause corrosion and the solvent recovery, many times not water, by the way. So enzymatic degradation can offer selectivity and naturally mild conditions. We all know most of the enzymes work on pHs between 6, 7, and some at 4, but not really much above or below that. And also they can very easily lower the activation energy for make these type of conversions. So in this case, I'm going to present you some enzymes that initially people may not think that are indicate for these kind of cleavages, but in fact they work very well. First are LAQVs. LAQVs are multi-copper oxidases that use oxygen and they oxidize phenolic lignin units. So these small here on below these units are very strongly bounded and form reticulates. And the peroxidase, in this case, the deep peroxidase, which the name comes from its very efficient decolorization properties. So these are based in central redox center, which is in, and it's active under a little lower pH, around 4, which is the ideal, and oxidize non-phenolic substrates. So together, they can attack these different components of biomass. But we have others, and these are the most recent discovered, maybe around a decade or 15 years ago when they start using this. So the LPMOs are copper-dependent monooxygenase, and they attack the bonds in the position 1 and 4 in cellulose. And the thing is that while the cellulose that used to work for this degradation, like endoglucanase and etc., are hydrolysis, they need water. LPMOs are use an oxidative mechanism. They use either oxygen or peroxide as co-substrate, and they actually cleave the cellulose from the center to the different directions, to left and right. So they start cleaving the cellulose in the middle of the cellulose. And another particular interesting is that they can be controlled by the redox environment. So all of these enzymes together, I mean, not only these three, but I'm going to talk about these three, can be used to make an enzyme cocktail that, by the way, are already used in the degradation. But in this case, cocktail of enzymes that we can control electrochemically and with precision, meaning that we can control very specifically the concentrations, the energy, and so on, and don't leave it everything in bulk and trying some, how can I say, empirical formulations. So these synergistic enzyme systems, this, of course, is an AI created image, but I think it's quite nice. So we have the LAQVs and the DIPs that can oxidize lignin and expose cellulose, and then we have LPMOs that can oxidize cellulose and increase the accessibility for the other enzymes that are included in the cycle. And in that sense, these are a very synergetic system. And as LAQVs and DIPs, they work, for instance, by releasing also oxygen and peroxide that can form radicals. This all together makes more easily to degrade to cleavage the lignocellulose biomass. So here you have a small overview of the mechanisms that are associated to the enzymatic cleavage of the biomass. And as you can see, they are quite complex and involve very different enzymes. And what we pretend is to control the LPMO here and also the peroxidase and lacase here, and together to help to this degradation in a much easier way. As you can see here, for instance, peroxidase, it uses hydrogen peroxide, and lacases uses oxygen. And one thing that is interesting is that LPMO also can use oxygen and hydrogen peroxide to its mechanisms. So, and also produces hydrogen peroxide, meaning that this is a very tiny, not tiny, how can I say, very complex balance in which the conditions, the concentration of each substrate can lead to a very efficient enzymatic catalysis, or can lead to some dead ends. And in nature, of course, is all works very well, but to reproduce it in the lab, it's not that straightforward. Also, by the way, LPMO works much better in crystalline forms of cellulose than in amorphous form of cellulose, while the others work much better when we already have amorphous biomass. So, starting with these new enzymes, let's say more or less new, and these have only one copper as catalytic site. They have highly conserved residues around the copper, and especially the phenylalanine 219, which is this one, I think. And it has, it's a big enzyme. Not super big, but it's quite a big enzyme. And the catalytic site, the copper, must be in copper 1 initially, okay? And of course, it uses polysaccharides as substrates as cellulose, as I already told you. This is a representation of the Streptomyces caudicularis that we have been used. And this is an enzyme that has special high redox potentials. So, as already mentioned, it works by cleavaging in the Cu, making C1, making a C1 oxidation, or a C4 oxidation. Okay, and it gives different products in the end, and this can also be tuned electrochemically. So, as I told you before, this is a very specific balance, because it starts with when you have copper 2 in when the enzyme is in rest and in presence of oxygen, and then we have the reduction of the copper 2 to copper 1, and then in the presence of the biomass of the substrates, they use oxygen or peroxide, oxygen peroxide, to make the cleavage and to make the conversion, but in too high amounts also gives an oxidative self-inactivation. And that is why here we have, as electrochemists, can have a role by just giving the amount of energy necessary to make one route or the other. So we have characterized LPMO in the lab. I'm going to show you just a few results, not extensively, for not boring you too much with this, but we have made the characterization of the wild type, and also some mutants that have changed the ligands around the copper in order to see what would be the effect of these changes in terms of the efficiency of the reaction, the electron transfer constants, and the redox potential. In principle, the higher the redox potential will be, the higher higher is the ease of the reaction to happen. Okay, so in this case we obtain around 200 millivolts, which were already expected, but we have just saw that when we change phenylalanine to an alanine, we do have higher redox potential and higher electron transfer constants, meaning that probably we'll have a more exposure to the copper, to the environment, and to the cellulose binding surface. And that is what we actually want to enhance the catalytic efficiency of the system. Also, by the cyclic voltammetry, and I hope to be able to talk about more aspects of electrochemistry in future talks. We can also attain constants and with these methods. For instance, we can attain the enthalpy and the entropy of the different processes. And here we can also see that this mutant is also presents a lower enthalpy of the process. Another thing that we have saw is that besides the wild type and with other controls that we have done, this mutant presents the higher oxidase activity. So in fact, it seems that of course, you can see here is the wild type, and here is the mutant, and you see that in the end, the activity is the same, but we can reach that much faster, okay? And so we believe that...
3 minutes, okay?
Oh, what?
Three.
Only, okay, I'm going to hurry up. So, sorry about that. So, let's go to deep peroxidase. I'm going to skip this part. You can also find this on the CHIB in 2022. We also characterized this one, and as you can see, we just... we have a very nice enzymatic activity. Also, a LAQV, the one that I was talking about, that works in synergy with the other enzymes. And also, we have also characterized some mutants and also the characteristics of the electrochemistry of the process. So, going to something more interesting. So here we have done some interactions among the enzymes, and we have discovered that the DIP can go and transfer electrons directly to the LPMO. Meaning, and we, in that sense, increase the efficiency of this enzyme. And as so, we are convinced that a cascade of these enzymes will be the best that we can have to really improve the process. So we can convert electrochemically driven the LAQV catalyzed oxidation of lignin, that then is catalyzed by DIP, that also uses the hydrogen peroxide. And then with this, and in the presence of LPMO, we can actually choose the value-added products that we have in mind. So very briefly, as conclusion, these three enzymes, and I'm sorry that I had to hurry a little bit, they can form, like we used to say, a toolkit that can be used as an alternative to the current acidic and alkaline methods, and enabling also the fine-tuning of the catalysis. And of course, this aligns pretty well with all the green chemistry and the global decarbonization goals. So I'd like to acknowledge my answer to the funding agencies. Thank you very much, and I'm really sorry to have done this in a very hurry way. I told you I'm not very well today, so sorry about that. Thank you very much.
Thank you so much, Cristina. It was on time. I have to apologize first because I should have said that now you are assistant professor here at the Department of the Chemistry here at Nova. Thank you for your presentation. Now we open for some questions.
So I guess everybody was completely satisfied.
Actually, I have one, and I apologize. If this is very not that smart of a question, but this is done in liquid state, right?
Actually, this can be done in both ways. In bulk, of course, in a liquid, in a solution, or adsorbed in electrodes. And this way, the adsorption gives us quite a lot of advantages. First of all, we can spare the quantity of enzymes that can be used. We can enhance the active area, so we can use smaller amounts of enzymes and have a huge efficiency. And actually, it was done by the two methods. Yes. Actually, these results was all in adsorption. On electrode surface. Yes.
Okay. I think then I will have to understand better that way, because for us working with cultural heritage, we have always the issue of solid state. So electrochemistry is very interesting for us, but then we cannot say it would be yes, hand in the air.
Yes, I sent my question from the chat.
Okay. So I have to find the chat. Can you ask the question?
Yes, thank you for this presentation first. I am in my work, that's why I couldn't join with my video or audio, I'm sorry. Thank you for your presentation again, but in my Master of Science thesis, one of the problems I faced in electrochemical detection was absorption. And did you face with absorption problem during your process? And what was that?
In this, adsorption can be an advantage or a problem, depends on the systems, right? So if you want to work on bulk systems and just to work with that, an adsorption can be a problem, okay? On the other way, you can use only adsorbed stuff and not having them in solution. And that was what I have done here. So adsorption for me for us with these systems are an advantage, not a problem. Okay. So it depends a lot on what you want to do and what is the system. Let me just give you an example. If I want to make a synthesis in bulk, for instance, an organic or an organic synthesis, and I use a platinum electrode, and if I have something organic, I will probably have a distortion on my electrode that will hinder the overall process in solution, okay? So that's an advantage. Here, I have absorbed the enzymes, so I don't have enzymes in the solution anymore, and I can just work from the surfaces with a very tiny little amount of enzymes, and also having at the same time the process running in the solution. Understand what I mean? I mean the absorption here is what I intend to do.
So did I understand correctly? Instead of making a coverage process extra, you use adsorption in this process.
This is very well because I didn't hear it very well. Can you repeat, please?
Yes. Instead of making extra coverage process into your sensor, you use adsorption into your advantage.
Yes,
did I understand correctly?
Exactly that. But this has sometimes the absorption of proteins and biological material is not straightforward. So it also needs a lot of optimization to be effective. I have a webinar about only with this type of stuff. Immobilization, maybe in another day I can immobilization for me by email, okay? And we can discuss.
So thank you so much. We'll now go for